Okay, class, next topic, next set of pages in chapter 2 of journal 3.5 are what happens when we take higher derivatives of the space curve. So we have our plane curve. We have a vector function. If it's 2 dimensions, we have a plane curve. If it's 3-dimensional, we have a space curve, and we can talk about higher dimensional things too. But mostly we'll stick with the physical applications here. So let's suppose we have this R3 space curve, right? And this is in a section in your book where we're going to start analyzing the path of a fly. So this is a fly's space curve. Let's see what happens when we take a look at that fly space curve. So I made a particularly a more interesting one rather than those like basic twisted cubics, helix. So let's look at a more interesting application where we've got definitely a lot of nonlinearity, some cubes, some exponentials, a polynomial function at ln. And then our range for t is from 0.1 to 5.6. Remember, we can't have a 0 or negative values in the domain due to this ln. And so let's see what happens when we take a look at this as a, take a look at this space curve in CalcPlot 3D. And okay, so I've entered a space curve, and this is the fly's first component t cubed e to the minus t, this polynomial in the second component ln t, but we need to change the domain. So notice now as it is graphed, though there's this discontinuity showing this like problem here when t is 0. And so let's go ahead and put our domain of 1.1 to 5.6, keep some orientation arrows, keep it in red. Okay, so enter. All right, let's get a better view. This is the usual orientation. Okay, so we see the fly starting down here. We can animate him as he goes along, see where he sort of goes quickly and then slows down. We can get a sense for that by animating the trace point. And now we're going to wonder what happens to this fly when we start taking, that's the r of t vector function. What happens when we take the derivatives? Well, we already know from the previous lesson that the first derivative gives our direction of motion. That is our tangent vector, r prime. And if we normalize it, we get the unit tangent vector, which is given by capital T of t, which is just a length 1 in the direction of motion along the fly's path, right? So taking this derivative, not hard, but the first one, right, you need a product rule. No problem here on the polynomial, no problem there. You get to this line, so you can pause the video to practice your derivative stuff from Calc 1. Make sure you've got that. Another way to check your derivatives would be with the tech tool like Wolfram Alpha. You can enter each piece and ask for the derivatives, or Symbolab does it as well and shows the steps. Just to make sure you can get to this line. This is also called the velocity vector. Remember, directions of motion, we have direction and magnitude. And so that creates a velocity vector. I know we got a lot of physics and astrophysics majors, so you guys are real familiar with taking these derivatives. Well, what happens if you take the length of the velocity vector? You get something called the speed, right? And this is going to be not a vector anymore. It is a scalar, right? Because speed is 50 miles per hour. Whereas here we have a vector. So just taking the length of the velocity vector gives you the speed vector, and that's just the length of the first derivative. But notice how messy that starts getting, right? Because you're taking a square root of the sum of the components squared. So again, it doesn't make sense to try to simplify that, because typically what you're doing is they might want to say, how fast is the fly going at time 1? Or you just plug in. Right here, plug in 1 for t, get a value. How fast is the fly going at time 3? You just plug in 3 to that mess. Or there's a nice way to ask Wolfram Alpha to evaluate when t, you type in this messy expression, and then you say, evaluate this messy expression when t equals 1. And it'll spit out the numerical values. You don't have to do any of those yourself either. It's just calculating work. Okay, continuing on, what if we take another derivative? The second derivative, also done component-wise, you take the derivative of the derivative. And so if you do that, some more product rules, you get down to here. The polynomial, some power rules. This represents the acceleration. So the second derivative is your acceleration vector. Now, let's talk about what happens. Let's introduce a new vector called the normal vector. And let's see, most books like to call this, I believe they call this with n. Let's check it. Yeah, n of t. And this is just taking your tangent vector, taking the derivative of that, and then normalizing that. So this is also going to be a unit vector, length 1, dividing it by its length. But let's take a look at that. We already saw that the unit tangent vector had this length in it. So for a particular t, that's not so bad, but if you asked for the unit tangent vector for any t, you can have a pretty messy denominator, square roots with some t's, and then you want to take the derivative of that, put that here, and then take that thing's magnitude. So this is going to get pretty messy. This one, somewhat messy. This one gets much messier. But let's talk about what it means geometrically. You have some really nice activities in this middle section of chapter 2 that'll help you visualize the tangent and the normal vectors. And then we'll often, unless they're very basic textbook ones, you'll do by hand. Most of the more interesting and challenge problem ones, you're welcome to use the tech tool. And I'll show you how to do those in a moment. Okay, so let's go ahead and see what CalPlot 3D shows us for these normal vectors. Okay, so our fly space curve is already in there, and we go to the gear setting and see some other things about this. We've already talked about the trace point, the trace vector. The velocity vector is your tangent vector. It's not normalized though, so it's not the capital T. It is longer than that. That's just your derivative. This one here. And you can show that. Let's just start with that one thing at a time. You can animate that. Black vector is your direction of motion. Notice that the length of it gets longer at certain points. Short there. So it's not going so fast. And we notice that the black dot was slowing down around this bend. And then it really starts to speed up. The length of this vector gets much longer. And it does speed up. So again, playing it slows down around the bend and then gets faster. And the length of that black vector is getting longer, which is representing when you take the length of the black vector, the velocity vector gives you the speed. So by getting its magnitude, you have the speed. Okay, so let's then show our acceleration vector. That's going to be now in green. So we have these two vectors moving through time, the green and the black. One represents your acceleration, your direction of acceleration. Notice your direction of acceleration. That green one is pointing towards the inside of this curve here. That is our A of t, which is also the second derivative, or double prime of t. Okay, let's take those off for a moment though and show our unit vector. Unit tangent vector is just the velocity vector shrunk to have length 1. That's also called the capital T. So we have lots of different notation as the capital T of t. And let's show our capital N of t, our unit normal vector. And let's show the labels on those. So one's in purple, that's the T tangent vector. The normal vector is in blue. And if we want, we can also show those equations, which is helpful. Those are the tangent vector is the top line here. The normal vector is here. We're not going to work on the B vector, which is the binormal. So you can ignore that last line. So we're just going to look at first and second rows and notice that it can compute those over time. And so it's really a calculator as well as we animate this. And we can animate it over its whole domain. And look at these two vectors. Now, do you notice anything about the relationship between the T and the N as we keep animating, between the purple and the blue? They actually always stay orthogonal. And that's a really neat feature and maybe you don't see it right now. Let me stop sharing the screen for a minute. The tangent and the normal vectors are always perpendicular to each other. So they're always going to be moving along the curve in this perpendicular manner. And it happens because if you were What's one way to check if two vectors are perpendicular? Get their dot product. If their dot product is what? They're definitely perpendicular. 0. If their dot product is 0. So you could check that these two things actually dot to 0, and it really just amounts to saying, checking if t of t dotted with its derivative equals 0, and it does. That's for my math majors, folks that have had 295. You could check that, prove that these two are they are by design perpendicular. And let's also go back to the screen share and show visually another thing about this relationship between the t and the n. So another nice feature is that we can show the normal plane. Okay. As we animate this. Now the normal plane is normal to the tangent vector. So the tangent vector in this example is purple. I don't have a purple pen. I got a close enough one. I got a purple and a pink. So the tangent vector is moving along in the direction of motion along this curve, and it always has a plane that is normal to it, right? And we can get that equation of the plane if we want by just, we have the vector, right? And we want to get the plane, we have the ABC, the normal vector for this plane. And so we can go ahead and get this if we want. And this is something that CalcPlot 3D can do as well, get the equation of this normal plane. But as we're moving through, we have this plane. Now, how many vectors live in this plane that are orthogonal to our tangent vector? Infinitely many, right? Any vector in the plane is orthogonal to the tangent vector, right? Because that's by definition what it means to be normal to the normal. So any vector in here is perpendicular to this one, but there's only one that is perpendicular and always points towards the curve of the space curve. So let's see what that means. So let's animate this one more time. The green plane is always what the normal vector lives in. It's also always perpendicular to the tangent vector. And notice how this normal vector, the blue vector, let me go ahead and maybe get the plane out of there just to clean things up a little bit. As we animate, notice that the blue normal vector always points towards the curve of the space curve. So when we're back here in the beginning, if you're riding a motorcycle, another way of thinking about this is to imagine you're at the black point and you're riding on a motorcycle, or very fast e-bike, whoops, sorry, I did not mean to do that. Which way would you be leaning? So if I start moving, I'd be leaning my bike towards the curve in the road. Now I'm upright, almost fully upright because the road sort of straightens out. And now I need to bend sharp towards the inside on my motorcycle to come around this particular turn. And then it sort of straightens out and I can come up. The road straightens and becomes almost linear towards the end here. So think about the normal vector as always pointing toward the bend in the curve of your road. So think about the space curve as the red space curve as a road. Think about the black point as you riding on a motorcycle. The purple T vector gives you the direction you would sail in if you were to, let's not think about this, fly off the edge of the road over the cliff. You won't do that because you're going to lean in the right direction. You're going to lean towards the normal vector, towards the bend in the road. Okay, let's see. Okay, so let's do, those are all the concepts associated, the key terms and the concepts. That was all for this fly space curve. I'm going to erase the board and we'll put up another example. So you don't need to watch me. Okay, let's look at this example. We want to find the tangent vector for any t and the normal vector for any t for this space curve, right? 3 components, we're in R3. What does this look like? Hopefully you recognize it's nonlinear, yes. This part would make a circle, you'd be running around, but then you add the t and you're wrapping around the cylinder. So this is our vertical helix we've seen several times. And we don't need to We don't need to visualize this, but if you like, it'd be a good thing to pause the video, go into Calclot 3D, get a visualization for what it looks like, and then we want to come up with an equation that represents the tangent vector. These are both unit, right? They're going to be length 1, so we're going to be normalizing them. And the unit normal vector. And we can do this just straight away with the algebra and calculus. The tangent vector is the derivative normalized, so the velocity vector normalized. Therefore, it has to have length 1. The derivative is, let's see, the derivative of cosine is minus sine, so that would be minus 2 sine t 2 cosine t 1 over the square root of the sum of the components squared. So that would be minus 2 sine squared t, minus 2 squared is 4, plus 4 cosine squared t plus 1, which is minus 2 sine t 2 cosine t 1, divided by, I can factor out the 4, and then I'll have sine squared plus cosine squared is 1, so I'll have 4 plus 1 is 5, so the square root of 5. Or another way of writing that is just, it's the derivative vector multiplied by the scalar 1 over 5, which makes this have length 1 by design. Therefore, if they were to ask you at any point t, what is the direction, the unit direction of motion, you'd just plug in that particular value for t. So you can tell them at t equals 1, t equals pi, t equals 10. You plug into this and get a vector. It would always be length 1, but it'll give you a direction of motion at that particular t. Now the normal vector is the derivative of the tangent vector normalized. Again, usually these are pretty nasty problems, but because I chose a helix, the sines and cosines make some of the simplifies things for us. And so let's see what happens with taking the derivative of the tangent vector and dividing that by its length. So it'll be in the numerator a vector, which is derivative of sine is cosine, so minus 2 over square root of 5 cosine t. The second component will be minus 2 over square root of 5 sine t. The last component of 0, divided by the length of this thing, which is going to be, we'll have the same thing with the sines and cosines, so we'll just have the square root of 4/5 plus 4/5 plus 0. So 8/5 square root. So this becomes, what is that, 2 square root of 2 over 5 times this vector minus 2 square root of 5 cosine t minus 2 square root of 5 sine t 0. Do a little more simplifying. Let's see. Oh wait, I have to, I should simplify this first. This denominator. I think I got ahead of myself here. So this would be square root of 8/5, which is square root of 8 divided by square root of 5. Those things will flip. Now they'll come up and be, the square root of 5s will cancel out, and I'll have minus 2 over 2 square root of 2 cosine t. Minus 2 over 2 square root of 2 sine t 0. Yeah. Okay, so some things cancel out. -1. -1. And again, that represents our normal vector for any t. You plug in a t, it'll spit out a vector, but that vector always points in the direction of motion. One last screen share. So I could enter our helix, 2 cosine t, 2 sine t, t, let's see, -6 to 6. There's our helix, vertical helix, and let's enter the normal vector and the tangent vector and show the labels and the equations. Okay, so that all looks good. As we animate it, the purples and the blues move through the domain, always pointing, t always points in the direction of motion, n is always perpendicular to that, and it's always pointing towards the curve as you move. And we gave the t and n for any t, and they're displaying it at a particular one. So if you're interested in t equals 1, you can enter that in the trace, and it'll move it up there to 1. It'll output in the upper left corner the t at 1, the n at 1, showing those as vectors, which you can confirm with what your computation was. So confirm your calculation with the calculation that CalcPlot3D is doing. Okay, that's it for this lesson. Next time, one last topic, really neat application. Then we're about halfway done with chapter 2. Chapter 2 is a long chapter, but there's a lot of neat stuff in here. It's extensions of things that you already know from Calc 1. And our next topic is curvature. So we'll be able to say precisely how curvy that helix was at a particular point, precisely how curvy that fly's path was at any point.